Hello. I want to talk about active magnetic bearings in contact with backup bearings. What are the magnetic bearings? Magnetic bearing is a type of bearing, particularly for rotating shafts, that uses electromagnetic forces to support the shaft with no mechanical contact. I will explain two popular types of magnetic bearings: active magnetic bearing and passive magnetic bearing. Active magnetic bearing is a type of magnetic bearing in which non-contact support of a shaft is achieved by using closed-loop control. Such bearings use attractive magnetic forces where at least part of the magnetic force is produced by actively controlled electromagnets. The active magnetic bearing includes a magnetic actuator, position sensor, and magnetic bearing controller with a control device, power amplifiers, and power supply. Most industrial and commercial magnetic bearings are of this type. Passive magnetic bearing is a type of magnetic bearing that does not require active control. While there are a wide variety of passive magnetic bearings, they have not found significant commercial applications due to low stiffness and low force density per unit surface area. An active magnetic bearing system supports a rotating shaft, without any physical contact, by suspending the rotor in the air, with an electrically controlled magnetic force. It is a mechatronic product that involves different fields of engineering such as mechanical, electrical, control systems, and computer science, etc. You can see a simplified active magnetic bearing control schematic diagram. The rotor is free to be suspended in X0 and Y0, which is at the center of the active magnetic bearing. The deviation of the rotor between the actual position X and Y and the set X0 and Y0 is detected by a non-contact position sensor, which is feedback to the control device. The control objective is to maintain the rotor near the expected values X0 and Y0. In this way, according to the deviation between the actual position X and Y and the set position X0 and Y0, a position adjustment command signal is produced by the controller, which is converted into a current by a power amplifier. The current is inputted to the bearing electromagnet coil to produce the desired electromagnetic control force Fx and Phi, which makes rotor stability suspension. Under certain operational conditions, a transient fault, overload condition, or disturbance may occur. Backup bearings or BB are therefore implemented in such systems to prevent contact between rotor and stator laminations. If the rotor makes contact with the backup bearing, the rotor dynamics may become transient or persistent in contact. In this project, rotor, BB contact conditions are investigated experimentally using a simulation of an active magnetic bearing system with a rigid or flexible rotor. BBs support the rotor while the active magnetic bearing system is not operating, but also limit excursions of the rotor during operation, such as in cases of power loss, component failure, rotor mass loss, or other significant external disturbances. Such cases may cause rotor, BB contact. Since BBs are functional components of active magnetic bearing systems, it is crucial to understand their influence on rotor dynamic behavior in contact cases, to minimize potential damage. This is particularly important as BB life and condition impact directly on the reliability of active magnetic bearing systems. BBs are used to protect the active magnetic bearings in the event of a system failure. Safety as defined by Schweitzer is the quality of a unit to represent no danger to humans or environment when the unit fails. BBs are used to improve the safety of active magnetic bearing systems. Active magnetic bearings can fail due to a fault in the active magnetic bearing system or due to an overload imposed on the active magnetic bearing. A BB is set up with a clearance from the rotor. Currently using half the air gap of the active magnetic bearing is the norm in BB design. BBs are divided into 5 main types according to their physical layout. The 5 types of BBs are plain BBs, rolling element BBs, planetary BBs, zero clearance BBs, and hydrodynamic BBs. This table gives a comparison of the different types of BB technologies. Rolling element bearings and plain bearings are the most commonly used bearing types. This project focuses on rolling element bearings since they could be easily simplified to represent a plain bearing. Thus, by developing a model for rolling element BBs, the model can later be simplified to also represent plain BBs. Pause the video and see the advantages and disadvantages of BB technologies. Important information of designing a backup bearing. When designing or selecting BBs, low friction is essential since higher friction forces could cause the development of destructive backward whirl. Good results have been obtained with ball bearings with coated rollers or rollers made of ceramics. No caging of the balls to reduce the inertia is also good practice. The lower inertia is essential when the bearing elements have to be accelerated toward the touchdown rotor speed. Selecting bearings with higher internal clearance to allow for thermal expansion is a good practice. The landing sleeve should be made of high-strength material and have a surface with low friction and great hardness. The support structure should be rigid to maintain alignment, and the BB should be kept clean from contamination. Special components should be designed for impact dampings, such as the corrugated ribbon design used in, or a damping ring as used in, or a compliant mount as used in some papers. Contact time has to be kept short to avoid overheating of the BBs, and the rotor should be actively slowed down or recovered by control actions. However, the optimal design of BBs still relies mostly on experience. A systematic generally accepted design procedure has yet to be developed. Safety can only be improved, never guaranteed. The proper design of any active magnetic bearing system requires the knowledge of all the dynamic loads that the system will experience in its planned life. The forces acting on a rotor system before and after the failure of a bearing system are given in Table 2. The three columns summarize all the forces acting on the rotor. The first column is the forces produced by the active magnetic bearings. The second column displays forces that are always present, namely the rotor unbalance and gravity. The last column is a summary of the forces produced by the interaction of the rotor and BBs after active magnetic bearing failure. The stiff nature of any BB model requires the initial values before the delevitation of the rotor to be accurately modeled, which means the events before the delevitation of the rotor should also be modeled. In the case of BBs, the factors that determine the initial values are the active magnetic bearings and the rotor unbalance. This means that the unbalance should be known and accurately modeled. This also requires the active magnetic bearing model to be an accurate representation of the real-world equivalent. Following the delevitation of the rotor, the next step in the modeling of the event is the determination of when contact occurs between the rotor and the bearing in a race. The size of the air gap needs to be known for each bearing. Although the air gap is specified during the design of the system, manufacturing tolerances on both the bearing and the rotor influence the size of the air gap. Should the stator be modeled, the BB moves relative to the housing after the first impact. This motion of the BB has to be taken into account to determine if contact is occurring. The forces on the rotor during contact need to be determined. These forces are highly dependent on the stiffness and damping of the bearing and the stator. This means that the stiffness and damping of both the bearing and the stator have to be determined with great accuracy. After initial contact occurs, the rotational motion of the rotor will impart the torque on the inner race of the BB, and this torque will cause the bearing inner race to accelerate. The acceleration of the bearing inner race will continue while there is contact and until the surface speeds of the rotor and the bearing inner race are equal. When the surface speeds are equal, the friction force of the bearing on the inner race will, in effect, be zero since there is no relative motion between the rotor and the inner race. There are, however, still rolling and internal bearing friction present when the surface speeds of the rotor and the bearing inner race are equal. The contact between the inner race and the rotor also causes the rotor to experience a translational force. The translational force causes the rotor to move inside the BB air gap radius. The translational movement of the rotor at the bearing locations is highly cross-coupled. Consequently, the translational movement at each bearing location influences the translational movement at all other bearing locations. The rotor model should accurately represent the real-world rotor to accurately cross-couple the BBs. The foregoing principles are discussed in greater detail in the rest of this video. Firstly, the overall model concept is presented. Secondly, an explanation of the translational model with the focus on the contact and stator model is presented. Next, the rotational model is presented with the focus on the friction model, the rotational dynamics of the inner race and rotor, and the modeling of the circularity of the sensing surface. This is followed by the introduction of the active magnetic bearing and rotor models used in the model. Lastly, the cross-coupling of all of the sub-models is discussed. The concept of the model is the division into simpler sub-models of the complex interaction between the rotor, the active magnetic bearings and the BBs. The main sub-models include a rotor model, active magnetic bearing models, and BB, stator models in the translational direction and rotational direction. A representation of the rotor, active magnetic bearing, and translational BB sub-models are shown in this slide. The bottom image shows a representation of the rotational BB model. The BB and stator are modeled using these basic elements as shown in this slide. The stator is modeled as a rolling element bearing mounted on a damper. The stator and the bearing translational models are inseparable. The vibrational characteristics of the BB and the BB housing are dependent on each other. If the active magnetic bearings are active, the rotor model receives the force exerted by the active magnetic bearings, and if the air gap is exceeded, the force is caused by contact with the BB. The rotor model uses these forces and determines the new position of the rotor within the air gap clearance. This means the BB model determines the force exerted on the rotor for a certain translational displacement or in velocity. The force determined by the BB model is used as input by the rotor model to determine the new position of the rotor. The non-circularity of the sensing surface influences the behavior of the active magnetic bearing. An active magnetic bearing controls the position of the rotor by measuring the distance to the surface of the rotor and then assuming that the center of the rotor is a fixed distance from the surface. This, however, is invalid since the rotor is not perfectly circular. The data obtained from the non-circularity of the rotor sensing surface is superimposed on the position data based on the current rotational angle of the rotor. The offset value is determined by using measured data and a lookup table. Adding the non-circularity at this location affects both the active magnetic bearing model and the BB model. This will facilitate further research on the effect that non-circularity has on the rotor dynamic behavior of the system during levitation and active magnetic bearing failure. The active magnetic bearing model is based on the model in some papers but simplified to ease the computational intensity of my model. The active magnetic bearing model as shown in this slide is the only representative of the bearing stiffness and damping. The actual model is more complex. A representation of the model for one axis of one active magnetic bearing is shown in the slide. This slide shows a typical layout for a rotor, with the positions for the active magnetic bearing, BB, induction motor, and position sensors. The position sensors are not in the same location as the active magnetic bearings, and therefore the measurement of the position is not accurate for bending modes and conical modes. The active magnetic bearing controller uses the position data measured at the sensor locations and applies force at the active magnetic bearing locations. This is represented in this illustration. In shown table, the rotor model inputs and outputs are given. The rotor model inputs are stated in the first column and the second column states from where that particular signal originates. The third column states the rotor model output and the fourth column states the destination of that particular signal. This table should be read while referring to figure 16. The rotor model determines the position of each of the nodes in the rotor model. The sub-models discussed in the previous slides are all interconnected. And this time explains how and to what each of these models is coupled. The coupling of each of these sub-models is illustrated in the slide. The translational BB models receive the current position of the rotor from the rotor model. The BB model also receives the friction force from the friction model determined from the normal force on the other axis. The BB models further send the forces determined by each BB model to the rotor model. The friction models receive the normal forces acting on the rotor and use them to determine the friction forces. They also receive the current bearing speed from the rotational BB model and send the current friction factor to the rotational model. The rotational BB model receives the perpendicular forces from the friction model and determines the speed up to work of the bearing as well as the slow down to work of the rotor. It also receives the current friction factor from the friction model. The active magnetic bearing model receives the current position of the rotor at the sensor locations and sends the forces acting on the rotor at the active magnetic bearing locations to the rotor model. The rotor model receives the forces acting on the rotor from active magnetic bearings and BBs and sends the current position of the rotor to the active magnetic bearings and BBs. It receives the current rotational speed from the rotational BB model. Test 1. Turn off active magnetic bearings at 7,000 RPM with the rigid rotor. You can see the RPM figure and rotor positions figures at bottom of the screen. And the top figure is the contact force between the rotor and backup bearings. Test 2. Turn off active magnetic bearings at 16,000 RPM with the rigid rotor. Test 3. By adding the load and unbalance, we do the test again. In this case, contact and vibration are increased. Even when the active magnetic bearings are active, the rotor strikes the backup bearings. This contact increase after the active magnetic bearings are turned off. The active magnetic bearings are turned off, and their force is zero. The rotation speed of the mechanical components indicates that the contact has existed from the beginning. The severity of the forces on the backup bearing has been existed from the beginning and has increased after the active magnetic bearing turned off. Test 4. In this test we will see a short simulation of the rotor rotation while its elasticity is increased.